Hi, this is Richelle Teeling-Smith, and I am coming from the University of Mount Union in Alliance, Ohio. And I'm going to talk to you today about computational thinking in introductory physics. And this is specifically for high school and early college physics courses. The work I'm presenting here today was done by my collaborator, Chris Orban of The Ohio State University, and myself. And what we're going to do is we're going to focus this time, this presentation will be focused on computational thinking in these introductory courses. So we have a recent publication that came out in the Physics Teacher, and I've included the link right here on this slide so that you can follow the link if you'd like and look that up to get more information about the content that I'm going to talk about today. But the idea here is that we are hoping to provide a helpful introduction to this topic for physics instructors, both at the high school level and at the early college level. So what is computational thinking? So this is a relatively new term that has recently been added into science teachers' learning objectives and science standards. So as recently as 2013, the NGSS included this statement: mathematical and computational thinking should be one of the 8 essential science and engineering practices for K through 12. But unfortunately, there's not really a lot of widespread agreement among members of the community about exactly what computational thinking is, or even how you would go about assessing computational thinking. These efforts are still maturing. So one excellent example of this is a conference I had the honor of attending last year in May 2019. It was an NSF-supported conference hosted by AAPT, and it was called Advancing the Integration of Interdisciplinary Computational Thinking in the Physical and Life Sciences. And there is actually a recent report that has come out from AAPT that kind of shows our findings from that conference. And Bob Hilborn and the other presenters today are going to talk about other pieces of that. And hopefully we're all giving you slightly different information. There's not too much overlap. But I'm expecting that he'll probably go into a lot more detail about the findings from that conference. Regardless, what we're going to do in this presentation is we're going to summarize what computational thinking means for a typical high school or first college physics class. And we'll find that teachers are already incorporating a lot of this stuff in their classroom. So I'm going to go with the definition. This is a very popular and widely accepted definition for computational thinking. This was developed by David Weintraub and his colleagues and published in the Journal of Science, Education, and Technology. So this is verbatim their definition. This is not something that either myself or Chris developed. But the idea is that we have 4 key categories here. One is data practices, so collecting, manipulating, visualizing data; modeling and simulation practices, so using models to understand a concept, to test solutions, etc. We have computational problem-solving practices, so preparing problems for computational solutions, just computer programming, troubleshooting, debugging. And then the last one is systems thinking. So the idea is investing, understanding relationships in systems, thinking in levels, defining systems, and managing complexity. So when you're reading through that list as a physics instructor, and I know when I read through that list, the first thing I think is I do a ton of that stuff in my classroom already. Of course we do, absolutely. That's not a big surprise because this definition that was developed in the publication I listed on the previous slide by Weintraub and his colleagues, well, part of that development came from conversations with teachers, and a lot of those teachers were physics teachers, so it's not a big surprise. We do these things in our classroom already. Modeling and simulation practices, PhETS interactives are used pretty widely. Physlit Physics is a great example. Physics modeling instruction is a wonderful example, obviously. So data practices, working with data, that's almost done in almost every physics lab, right? Computational problem-solving practices, this is the more traditional category when I say coding, debugging, computation, that's kind of what you're thinking of. And then the most abstract of these 4 categories is systems thinking. And the idea is you're saying, I'm going to solve some sort of a problem that's really hard to solve analytically. And the one that we like to use, you might find in your first physics course, would be finding the air drag on a projectile. And so you have a lot of competing forces acting on a system, and the forces are changing in time, and so you kind of have this iterative process. It's very natural for this type of problem. And so having simulations designed to model these situations with these complex interactions, that's what we would call systems thinking. And so, of course, we already do a lot of these things in our courses, and a lot of these things already naturally fit with the typical learning objectives we're trying to satisfy in a physics course. So, if I'm an instructor and I'm already doing these things in my classroom, I might ask the question, so what can computational thinking offer physics instruction? Or other ways to phrase this question would be, how does this help the mission of an introductory physics class? Or when we're integrating computational ideas, what are we trying to do? What's the point? Why are we doing this? And so if you read more deeply into the paper that Chris and I published in the Physics Teacher, we kind of hit on a few key points that we're adding to this discussion. The first thing is you say, well, computation itself is valuable in introductory physics because it's an integral part, it's a foundational part of physics as a discipline. Right? If we don't include computation, we are not showing students what it is like to actually do physics. Physicists use computation and simulations and develop simulations all the time in their work, right? So you'll be leaving students ill-prepared for future careers. And that can be inside physics or outside of physics, and I'll talk about that a little bit more. One thing to think about is that, I said, well, what does a physicist do? And most of our students aren't going to go on to be physicists. And they're not going to become, they're not going to go into computer science or be programmers. They probably won't need to sit down and design and build large pieces of code and write that on their own. That's not what most people in our classroom are doing. Most people in our classroom are headed to technical careers. They might be going into engineering. They might be going into the medical field. And so they don't need these advanced programming skills necessarily. But what they will do is they will use sophisticated simulations, right, to model all kinds of phenomena. Traffic patterns, heat flow, maybe for engineering. Those are great examples. And so the idea is that they kind of need this early start to this kind of skill set that they would need to basically be proficient and be competent in those fields. And so we could say setting up code or a commercial program to accurately simulate a physical system it's not an easy thing to do, and students need to have an understanding of the subtleties of that system. Another way to put it, so helping students understand the difference between what we call math world and computer world. And so to kind of supplement this slide here, I'm not just going to read the text, I've included the figure from the paper. So, and you can also see the caption at the bottom, which is taken directly from the paper. So the idea here is that we're looking at teaching students the difference between math world and computer world, the difference between the analytical problems that they would do in class, the equations on their equation sheet that they have in class, and then what they need to do to translate that to a computer program that will actually solve this problem for them. And students don't always have a very natural understanding of the iterative process of computer programs. And so here we're looking at this figure. These are actually two students that came from the University of Mount Union. Those are my students that recorded this video. This is a clip that comes from the STEM Coding YouTube channel. If you aren't already subscribed to it, you should go ahead and go do that. But the idea here is that they're using these kinematic equations from physics class, and they're describing how to make this translation, how this equation for your final position, knowing the velocity in the time, is translated from math world to computer world, right? And so this is not necessarily an intuitive or easy thing for students to do. What else? So another thing that can be said is that it's kind of focused on sense making, right? And Chris and I are certainly not the first people to use the term sense making. This is very well established in the literature, but the idea is that, we're kind of, the students will go through and they create a program and they debug a program, and it challenges their intuition. They type something out and they think it's going to work, and they run their program and it fails, and they have to figure out why, and then they kind of go through this step-by-step process to sort it out. So overcoming that challenge is a type of sense making for the students. And so this is basically just providing a new form of sense making in physics. And then, of course, last, computation is another representation in physics. We've asked students to look at diagrams, to see an equation sheet, and this is a really well recognized idea, is that, there's got to be a lot of representations for the students to see and to understand a concept in class. So computation provides yet another avenue for that. So I've talked a lot, probably for a little too long, but what I want to do next is give you a couple concrete examples. Those are all very abstract, right? So a few concrete examples. So here I'm looking at, this is actually a screen capture from a activity in the STEM coding program. It's called Planetoids with Momentum. And so here we're seeing this little triangle is our ship. The ship collides with the planet. The planet is kind of like a blob of goop. And so they collide and they stick. And we ask students to go through. We give them a code that's not quite functional, and we ask them to develop the correct code for this kind of two-dimensional conservation of momentum. Now, the correct code is shown right here on the screen. And the idea is that students are going to go through, they're going to measure the the final velocity, check that it matches their expectation based on this problem. Now, one of the things that we're doing, or that we do, is we ask the students to look at this statement, right? So this statement for the velocity of the ship versus the velocity of the planet. And when they look at this, they see it, and this is the equation straight from their equation sheet. So when they look at their equation sheet for conservation of momentum, that's what they would see for these two objects. And they're going to copy this into their code, they're going to run it, and they're going to find out that it's wrong. You can't write the problem this way for a computer program. And students don't automatically look at the code and think that this isn't going to work, because they're not thinking about the fact that the computer program is going line by line. And so the idea here is that this iterative nature of the computer program, this is them kind of becoming, gaining a better intuition, or developing some intuition for how computer simulations can be very different than the problems that they're doing on paper in class. Here's another concrete example. It comes from a different group. So this is coming from Integrating Numerical Computation into the Modeling Instruction Curriculum by Danny Cabero and his group. And so this is actually a VPython implementation of projectile motion. And so you can see a little bit of the code that's included on the screen, and it kind of says, ask the students to go through, develop the code for projectile motion, and they're going to find that this is an approximation, right? So this is a perfectly legitimate way of representing projectile motion, but it's still an approximation. And after many time steps, when the position and the velocity are updated, they're going to find that the solution starts to deviate from the analytical result, which you would get from using the equation that's right here on the screen for the final position. And so it strays from the analytical result, and they're asking students to kind of investigate why. And this kind of comes down to learning a little bit more about the Euler-Kromer integration scheme, but not specifically that integration scheme, but just understanding how, as the computer is calculating these values, what is the difference, what is the computer doing, and in what ways is it correct and which ways is it incorrect. So this is just another concrete example. So I want to go ahead and stop because I'm just about out of time, but I did want to include a couple other follow-up ideas here. So one of the more interesting things you can do when you're thinking about integrating computational thinking into your classroom in new ways, in ways different than the ways we already do it, right? Is to ask students to develop a code to model a new situation in the real world. And so what they've done here is we have kind of a proof of concept kind of direct measurement video, and then the idea is that you would build your simulation in the foreground and have the video in the background, and you're testing whether your simulation that you develop actually aligns with the motion that you see in real life. And so there's a link to this demo that's available. I included the link right here on the screen. And so the idea is the students can record slow motion videos and then develop the code to simulate the motion they see in the videos. So I'm just including a screenshot from the paper right here. It also includes the caption for the paper. And so the idea here is that you have the actual video of the motion on the screen of this person sitting on a small cart. They use a fire extinguisher and it propels them across the screen. And then the white circle is the simulated object. And then the students would develop the code to make the object move with the correct position, velocity, and acceleration across the screen. Okay, so to end this, I hope that everybody will find some time to come to the live question and answer session for this session on computational thinking, because I think that the discussion will allow us to go a lot deeper and to kind of hit on some really interesting points. I want to acknowledge some of the funding that supported this work. So we had the AAPT Makers Award, the OSU Connect and Collaborate program, which is an internal grant, and then of course the wonderful discussions that we participated in May of last year in College Park, Maryland, on the workshop on computational thinking. Where can you find us? So STEM coding activities, we have our own website, so you can go and look up the STEM coding project. Our activities are included on the Hour of Code for code.org. And also we have our stuff on Pickup as well. So there are some links there that hopefully can be useful and help you find our activities. And also, well, okay, looks like the video may not play. That's okay. Well, we're just going to have to go with it. And so there's a STEM Coding YouTube channel. Oh, there it comes. Wonderful. Okay. Okay. Now I have the audio in my ear. I hope you can hear it as well. I don't know. We'll find out. All right. So anyway, that was a little advertisement, but just, we have this STEM Coding YouTube channel, and it's a really great resource for teachers if they want to use these modules in their classroom. And so the idea is you should go check it out and you should subscribe. All right. So if you have any questions, come find us at the live question and answer session. My email address and Chris's email address is included right here. Thank you for listening, and I hope to talk to you soon.